Every time you look down a long corridor or a road stretching to the horizon, your brain does something remarkable. It finds the point where parallel lines converge. That's the vanishing point. And teaching a neural network to do this reliably has been a surprisingly hard problem. Here's why and how a clever injection of geometry fixes it. So standard deep learning approaches to vanishing point detection work fine if you have massive labeled datasets, powerful GPUs, and your test images look a lot like your training images. Change the camera, switch from indoors to outdoors, or cut your dataset by 90% and accuracy collapses. The root cause? The network has to learn geometry from scratch every time from data. That's wasteful because we already know the geometry. Lines in 3D space obey rigid mathematical rules. So the question becomes, can we just tell the network that? So the first piece of injected geometry is the Hough transform, a classical technique from 1970s. Here's the intuition. An image is a grid of pixels. A line in that image, so each of these lines, they can be compactly represented as two numbers, an offset and an angle. It's polar coordinates. The Hough transform is essentially a vote. Every pixel that might belong to a line casts a vote for which line it belongs to. Lines show up as peaks in the vote space. So what this paper does, it make the Hough transformer differentiable and embed it directly inside the network. So we are combining the classical computer vision with modern deep learning by making Hough transformer differentiable so that we can perform gradient descent. So instead of the convolutional neural network blindly learning what the line is from pixels, it gets a structured line detection module baked in. The network learns features. The Hough module converts those features into explicit line representations, clean separation of concerns. Now you have lines. How do you find vanishing points from lines? This is where Gaussian Sphere comes in, and it's an elegant idea. Imagine placing a unit sphere at the camera center. Every line in the image, when extended to 3D, defines a plane passing through that camera center. That plane slices the sphere along what's called a great circle. The key insight: if multiple lines in the image share a vanishing point, their corresponding great circles on the sphere all intersect at the same points. So this is how we define what is a vanishing point using Gaussian spheres, and this is the calculation we make. So vanishing point detection becomes finding intersection clusters on a sphere, a much more constrained, well-behaved problem than searching the unbounded image plane. This also naturally handles vanishing points outside the image frame, which is a real headache for pixel space methods. A sphere is sampled using a Fibonacci lattice, a uniformly distributed point cloud, and spherical convolutions via edge convolution, and then localized via great circles cluster like this.